Welcome back, AP 14.5. How is temperature going to affect the rate? So now we're finally changing temperature. So AP Daily 5.5 and 5.6. These are two big videos. Each one has several learning objectives. We're going to conquer the energy profile, the activation energy curves. Some of these where it talks about elementary reactions, we're going to get to in 14.6. So it'll be the next one. So take a minute, read the objectives, make some notes, highlight, annotate, and then when you're ready, continue on with me. Collision model. So we actually have a model as in a graph to help us understand how temperature can affect a reaction. So in an elementary reaction, successfully produced products, you have to have reactants that have to have enough collisions, successful collisions, to initiate the bond breaking and bond making process. You got to have collisions. It's always collisions. Successful collisions must have enough energy to overcome the energy barriers and orientations that allow the bonds to arrange in the required matter. Remember the very first video, we talked about collision theory. And there were 5 items that needed to happen, and all 5 items must occur for a reaction to happen. Well, we already know you need collisions. We know you need energy, but what about the orientations? Okay, so we talked about in the very first video, but we're going to now understand what does that mean. So collision model, this is how we explain. For molecules to react, they must collide. The greater the collisions, the faster the reaction, the faster the rate. The more molecules, aka moles or concentration, the greater the collisions, the faster the reactions. Okay. Now, what happens if you change temperature? If you change temperature, you have more energy, more specifically kinetic energy, available for the molecules, and then they'll not only collide, but collide more frequently. The reaction rate should increase with an increase in temperature. Okay, so that's what we need. So how does temperature relate to rate in like an everyday type of experience? So most reactions speed up as temperature increases. Okay, ever think of glow sticks? Okay, we call them back on the East Coast nightsticks, glow sticks. It's an actual chemistry process called chemiluminescence. Chemiluminescence, it's a reaction that produces light. So basically what happens if you take like a glow stick, a light stick, and you place one of them in water, one at room temperatures, remember that's about 25 degrees Celsius, and one in ice, okay, about 0 degrees Celsius. The one that's in room temperature, because it has more energy than the ice, it'll actually be brighter. So the luminescence, because it's brighter, it'll actually fade more quickly in the warmer water than the cold water. So the higher the temperature, the faster the reaction, the brighter the light. But unfortunately, your glow stick will fade faster. So it won't last as long, okay? So what some people do when they get like glow sticks, like those necklaces that glow, they'll put them in the freezer, cool them down to make them last longer, okay? So if you put it in hot water, like maybe, close to boiling water, oh, you're going to have the most energy, the most kinetic energy, which means it's even going to die out even faster than the room temperature. So how does relationship with temperature affect the rate? Well, the rate law, remember when we wrote a rate law? K concentration to some power. Well, there's no temperature in it, okay? But temperature does have an effect because it's on him, okay? So rate is not in the rate, temperature is not in the rate law, but it's correlated to the rate law because of K. You have to keep K constant so that way you can determine the rate. If you change temperature, then you have a new K. So if temperature changes, you have a new K. And then you substitute that new K into the reaction to find. So if you new K, then you're going to have a new rate. Okay? So let's look at how a reaction actually can happen, but also make it faster. So there's a number of different things that you can change to make a reaction faster. We explained the concept of collision theory, which is what we did in that very first video, and how it can be used to explain the effects of 5 different factors to make a reaction go faster. So first, collision theory. What is the whole point of the theory? Okay? So collision theory states that for a reaction to occur, particles must collide with the correct orientation with enough energy. So you have to have energy in the beginning. Different factors affect the rate of reaction by affecting the frequency of collisions and the proportion of collisions that have enough energy. Okay? So what happens is with orientation, you have to make sure that the molecules line up in a certain way. Now remember, we can't see this stuff. Okay, we're microscopically, we're assuming that they are lining up in the correct orientation. So something like this would be a correct orientation where they line up. Something like the second picture, it's not going to react in the correct orientation. Or something like this isn't going to have enough energy. So maybe you have the correct orientation and energy, but maybe they're not lined up in the right way, or maybe they don't have enough energy. So you have to have both for the reaction to occur. Obviously, let's crank up the concentration because you now have more moles in that same volume. Okay? So when you have more moles, you have more collisions. And with increasing the concentration reaction in the solution, it increases the rate, which means you have greater particles that can react. And with greater particles, you have more collisions. We already talked about increasing temperature. Okay? Now, I want to go back to the learning objectives. There is a curve. We talked about it in chapter 11. Okay? The Maxwell-Boltzmann distribution curve. It looks at temperature and collisions. So this is that curve right here. So we're going to label it the Maxwell-Boltzmann distribution curve. Okay? We, in chapter 11, we looked at molar mass and we looked at temperature. Okay? We're just looking at temperature in this chapter. So with temperature 1 versus temperature 2, so right here, whatever your temperature 1 is, let's say temperature 2, we added 20 degrees with it, which means it's hotter. Okay? So the particles with energy required to react. But because now you're hotter, you actually have more particles that can collide because you gave them more energy. And because you gave them more energy, you have more particles that can react. So increasing temperature increases kinetic energy. The increase in frequency of collisions, a greater proportion of collisions that have enough energy to react. So, ladies and gentlemen, it's all about collisions, energy, temperature, orientation. Okay, you got to have it all. Some other ones we talked about this in the beginning of the very first video, surface area. Whether you had like powder versus like pellets. Okay, so that powder has greater surface area because you broke it down. Okay, with pellets, you're only able to react on the surface only. Okay, so you limit your self reactions. So increasing the surface area of a solid reactants increase the number of particles exposed, and they're available to react. And as a consequence, this increase in frequency of particles makes the rate go faster. Changing pressure, okay? Increasing pressure. You can even think of it as decreasing volume, aka gas law, more specifically, Boyle's law. So if we start changing the pressure of like gases, increasing pressure, notice what happens when we increase pressure. The volume is decreasing. We're bringing the gases closer together. And what happens when you bring them close together? More collisions. And that's what makes the reaction faster. And then the last one we talked about also in 14.1, a catalyst. So remember a catalyst, it's a chemical added, okay? But remember, there was a key part to it, which we're going to get to in the last video. It's a chemical added, but it's unchanged. The actual chemical is unchanged in the reaction. But it's added to make the reaction faster. He takes no part in the actual reaction, as in changing the chemicals. That's what I mean by chemical unchanged in the reaction. Oops. Okay? But he's only added to make it faster, and then that increases the rate. So what happens is, this is the graph that we're going to be looking at. With the catalyst, you actually have what's called an EA value that's lower. It goes from reactant to the top of the curve. And the lower the EA, the faster the reaction. But without a catalyst, you actually have a larger EA, which means the reaction is slower. Okay, so we're going to get to this in this video. So a catalyst, it provides an alternate route on how you get there. And it lowers something called activation energy, this capital EA. This means that the particles' collisions need less energy in order for the reaction to occur, making the reaction faster. Okay, so what is this EA part about? But you're going to see the catalyst come back in the last video, 14.7. Okay, so let's look at an example of why a chemical reaction needs energy to initiate the reaction. So students need to understand, this is AP talking to you, that chemical reactions consist of many smaller steps to produce the overall reaction. Just unfortunately, our eyes can't see all these steps, but we do it on paper. So each step's involved either gaining or losing energy, resulting in a net loss of energy called exothermic, or did it gain energy called endothermic. Consider the reaction of the rearrangement of this molecule, okay, which is called acetonitrile. It's called 3 H's with a carbon, so it looks like this. Has 3 H's, bonded to a nitrogen, triple bond carbon. This is very, very strong. When you have what's called a triple bond, very strong, which means it needs lots of energy to break it. Single bonds, they're not strong. They don't need a lot of energy, okay? So let's look at what this is all about, okay? This is what's called an energy profile. You could even call it an activation, because it's all about activation energy. Profile, which is a fancy way of saying graph. Okay, so activation energy profile. You have energy on the y-axis. You have reaction pathway. Now remember, reaction pathway is not time. Okay, it's how the reaction went from the beginning to the end. Okay, has nothing to do with time. What path did it take to get there? Okay, so make sure you label it reaction pathway. For the y-axis, you may even see the word not only energy, but you may see the word potential energy. And potential energy is the energy at a particular point in position, okay? So right here in the beginning, okay, and it should be connected right there, this is like our starting energy, okay? So right here at the origin, this is the reaction hasn't started yet, okay? Basically, it's the beginning. So in the beginning, all you have is this triple bond. That is your reactant, okay? That's all you have, okay? What we're trying to do is it looks like this right here. So I'm going to label this. This is my reactant. So we're going to make some notes on here, okay? In this case, we only had one reactant. And I'm going to make a product. Now, it looks like the same, but what happens is these two, they swap places, okay? Now, why does that matter? Because what happens is we have to break bonds to make bonds. How much energy is needed to break this bond so that way they can swap places, okay? So this is what the product will be. Oops, carbon, triple bond, nitrogen. So there is our product, okay? So that arrow right there is how much energy is needed to break it. And so then the next question is this bond, how much energy was needed, or actually it's not even needed, you're going to see what happens, is actually it's released. When you form bonds, you release energy. When you break bonds, you need energy. So this need to break and this release to form that bond. Okay? So in the beginning, all we have is a reactant. Okay? So then the reaction goes about and starts to proceed through a pathway. So right here at the origin, now the reaction has started, okay? And as you see, energy has not changed, okay? But then, remember how we talked about you need energy to get the reaction going. So then you start to see an increase in energy. So the reaction is gaining energy, but you haven't really done anything yet. You just need energy to get it to go. So what happens is this bond, it starts to bend, okay? So when the bond starts to bend until the CN single bond breaks, okay? So right here, we're trying to break this, okay? So then that way it can start to rotate, okay? And once it starts to rotate, you're going to get all this energy, gain. So all this is all positive energy. And then you get to the top of the peak. Now the top of the peak, okay, is called the activated complex, okay? But what about this energy, okay? So what is this energy called to get the reaction started? Well, it's called activation energy. So the energy required for the twisting and the breaking of the reactant bonds, okay, just the bond that you're trying to break, okay, is called the activation energy, okay? So in this case, they're trying to break that bond right there, not so much the triple bond. So I'm going to erase these lines because they were trying to break this bond, okay? Oops, energy needed. So please fix that because it looked like they were trying to break that triple bond, okay? So what energy is needed to break a CN bond versus forming a CC bond, okay? So all this energy is EA, okay? And EA is always positive. And why? Because you need energy to initiate the reaction. You have to have energy in the beginning, okay? Then you get to this point in time, the top of the peak. You have broke, see that dotted line? That means the bond is officially broke. Okay? And then you get to it's kind of like a roller coaster. All right, now I'm getting ready to go down the roller coaster. And notice what happens with energy. You are releasing a ton of energy. So releasing energy. Okay? And energy is just going down, 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 down. And what's happening is, see right there, we're getting ready to form that bond. Okay? And remember what happens when you form bonds, you're releasing energy. So releasing energy, since that CC bond is getting ready to form. Okay? And this energy right here, reacting, gaining energy, because I need energy to break that CN bond. Okay? Always need energy to break. Okay? So then that C triple bond N, it's just rotating, rotating until it gets into the place that it wants. That's why it's called energy of position. And once it gets into the correct orientation, position, then you get your products. And then it's just flatline. Okay? So EA is always positive. It's that energy needed to initiate the reaction. But what about this delta E? Well, AP lately has been calling it delta H. Now, do they mean the same thing? No. Delta E is change in energy. Delta H is something called entropy. It has to do with heat, okay? Exo and endo, okay? They want you to use delta H because entropy has to do with endo and exo. And I'll get more to that in just a second. So what delta E is, and you're going to see the equation down below, is they take the difference, the energy from the reactants right here to the energy of the products. Okay, so it's looking at how the energy reactants versus the energy of the products. You had more energy. Notice this value, and I don't have any values. Okay, so if this was 0, I know right here, maybe this is like 2 kilojoules. Maybe this energy right here is like 20. I know for the reactants, I had more energy in the reactants versus the product. I had less energy. Okay? I actually lost energy. And because what you had in the beginning, and now that you're over here at 2 kilojoules of energy, you lost energy. Okay? But what AP wants you to do, they want you to correlate it to delta H, which delta H has to do with heat, okay? Which that is the only term you can correlate to exo and endo. So because I lost energy, I lost heat. And because I lost heat, that means this reaction was exothermic, okay? I gave you a lot of information, and let's do some review before we do an actual one together, okay? So activation energy, it's that energy needed to initiate the reaction. Molecules must have energy to react. And why? Because bonds need energy, okay? To form products, bonds must be broken, and broken requires energy, endothermic. Always positive. So notice on that graph, that EA, always positive. Always need energy to start the reaction. So to determine the EA, it's the energy at the very tip. So here's your equation. It's the energy from the tip down to where the reactant started. Okay, so that's why it's always positive. Your activated complex, it's that difference in energy between the reactants and the top of the peak. So the activated complex is just that point in time. It's that maximum energy that you have to break that bond. And actually, we're going to change that too. So the maximum energy between the reactants and the top of the peak. Okay? Now, like I said, AP's been labeling it delta H, but a lot of our practice problems have delta E. Okay? They want you to use delta H because delta H is a term that's called enthalpy. You're going to see it in chapter 5 and 19. Enthalpy has to do with heat transfer. And because enthalpy is about heat transfer, it is the only term you can use for endo and exo. You can't use it with energy, okay? Energy has nothing to do with exo and endo. So if you see delta E, that's okay. So with our delta H, we're going to be taking the energy value that you had on the graph from the products minus the reactants. So notice in the graph that we had right here, we ended up with a lower energy number, so maybe it's a low number, minus a large number, a big number, and that low minus large, that's what's going to get us a negative value, and that negative value means exothermic, okay? And we're going to use some values in just a second. So that delta H, it's the only one that actually can be positive or negative, whether it's joules or kilojoules, whatever AP wants to use. But if it's positive, that means the reaction gained energy, okay? And if it's negative, it means it lost energy. And actually, I'm going to be fixing this. We're going to say the word heat. It lost heat because we're talking about delta H, or did it lose heat? Okay, negative delta H. Notice that delta H has no effect on the reaction rate because temperature didn't change, okay? So as long as we don't change temperature, our delta H, no matter what, will be the same for anything. So in summary, the change in energy, okay, or as we're calling it now, delta H, is the difference between the reactants and the product. The activation energy is the difference in energy between the reactants and the transition state. Our EA, the rate depends. This is big. Rate depends on EA. The lower the EA, the faster the reaction because now you have more particles with enough energy to make that change. Okay? Notice if the forward reaction loses energy, okay, which is exo, which is the reaction that we had, it lost energy, exo. If you what's called flip the reaction, then the reverse will gain, and it's called endothermic. And that's what we're going to look at right now. What happens if you flip the reaction? So let's do an example problem, okay? So I'm going to keep this, I'm going to actually minimize so we can keep both of them on here. That didn't do very much use right there. So I'm going to drag this down some so I can look at my picture. There you go. All right, putting it back. Okay. All right, it'll be all pretty for you guys when you get it. All right, practice problem. Use the following activation graphs to answer the following questions. Okay, so this reaction right here is called the forward. Okay, so let's say this is A makes B. Okay, so this is called the forward reaction. Okay, what happens if reverse is called flip? So now B is your reactant and A is your product. Okay, so we call this the reverse reaction. Okay, so potential energy, reaction process, maybe you can even call it pathway, just not time. Okay, so you start with, and I wish these curves actually started at the 0. So here's my A. And my A starts, and it's doing its thing, but it hasn't broke anything. You haven't done anything. And then it starts to gain energy, okay? So this activation energy, this blue line, is the energy from the reactant to the activated complex. And the activated complex is when you have broken whatever bond that is needed to break in the reaction. I didn't say every bond. You just broke the bond that you're trying to break. Okay? So that activated complex, it's that maximum energy. okay, that's in the profile. And then once you broke it, then it starts to rotate, okay? The molecule starts to rotate and change positions. You can't see it because it happens too fast. But in this part right here, you're losing energy. And in this part, we're gaining energy. Okay? So as you're going down this roller coaster, and it goes down, 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 until you get to a point, and then it flatlines, now I made the product. So what EA, or the delta H, now that we're going to label it delta H, is from the reactant to the product. So that energy from the beginning to the energy in the end. So we're going to call that delta H. Okay? Now EA is always positive. Okay? And my delta H, in this case, I had more energy in the beginning and I lost energy in the end. So that means my delta H, this value, is going to be a negative number. And because it's negative delta H, that means exothermic. The whole reaction in the end, okay, think of it like final minus initial, if that helps you, final minus initial, it lost energy. So we call that exo, okay? On the flip side, what if you actually start with B as your reactant, okay? And then you are gaining energy. You're starting to rotate. You're gaining and gaining and gaining. And then you get to that point in time where you have broken your bonds. So your activated complex. Okay. And then you start to lose energy as you go down. So my EA in this case, notice right here, my EA versus this EA. This is a new EA value, okay? It's completely different, but regardless, this one's positive. This is still going to be positive, but this is going to be a larger EA value because notice that arrow. It's still reactants to the activated complex. Then I lost, and then I formed my product. Well, notice right here, my B was low in energy, my A is greater. I gained energy. My whole reaction gained energy, gained heat. So that means endothermic, okay? So this delta H will be positive, okay? So what happens is, in one case, the forward reaction is exo, but in the reverse, it's endo, or vice versa. When you flip equations, EA, we'll call it EA1 versus EA2, okay? They're going to be new values. Just one will be bigger than the other, okay? But always positive. What happens to delta H? Delta H, either whether it's forward versus delta H, delta H reverse, it's what we call a flip of the sign. One is just going to be positive, the other one's just going to be negative, but it's the same number value. Just one is positive, one is negative, okay? So let's do an actual scenario with numbers. So for example, if the first graph had an EA of 45, okay? So let's say this EA was 45. Let me do it in a different color. We'll go green. So this EA is 45, and it says 45 kilojoules. And my delta E, that looks like a negative 30 kilojoules. Okay, so negative 30. What would be the new EA and the delta H for the reverse? Remember what I said right here for the delta H, forward and reverse. Same number, flipping the sign. So if this delta H was negative 30, well then this delta H is going to be positive 30. Okay, that's the easy one to figure out. Negative versus positive. But what happens with the EA? Notice this lengthened line. this lengthened line right here, this blue line, notice right here, it's the same length, but added together, okay? So this new EA, what you do is you take the 45 added to that 30, not negative 30, because remember, it's both these values added. So added to that 30, and you're going to get 75 kilojoules, okay? So in one case, your EA was 45, in the other case, your EA is 75. Well, which reaction is fastest? Well, the forward is the fastest, and why? Remember, we set it up here in the summary, okay? The lower the EA, the faster the reaction. So the lower the EA, the faster the reaction. Okay? So, another scenario. The reaction pathway profile. Here's another, actually I saw this graph on AP Chem before. According to the graph, this is the decomposition of hydrogen peroxide. So hydrogen peroxide broke apart and formed water and O2. Is the decomp reaction exo or endo? Well, notice where you started and where you ended. Okay? I have higher energy in the beginning and I have lower energy in the end. That means this reaction, the overall reaction, lost energy. So that means my delta H, okay, or this process is going to be exothermic. Because since the reaction lost energy, okay? Can you label your EA? Well, remember EA is from the reactants to the activated complex, okay? So right here, you just draw this little dotted line. And then that right there, there's your EA. Okay, and we know it's going to be a positive value. And then your delta H, remember, is from your reactants to products. So since I'll do it in red. So reactants, if you want to draw your line over here, or you can just draw it right on top, whatever makes sense. But from right here, this is where my reactants also were. So reactant, and my products ended. This is where sketching is very important. And my delta H would be this value. From here to here, and it's going to be a negative value. Okay? And my activated complex, that's where everything has been broken that needed to be broken, is my activated complex. Okay? Would this be a fast reaction? Well, probably, because this looks like a very low EA. Probably a fast reaction. Don't know without any numbers, but by looking, looks like it's probably a fast reaction. Okay? All right, AP, I'll see you on the next one.